Hello everyone, Joshua's here to help you learn about this LEETCODE problem. Oh wow, that's so bad grammar. I've got to redo this again, guys. Hello world, Joshua here. I'm going to teach you how to solve this problem, maximum depth of a binary tree. And if you don't know how to, if you don't want to solve this problem by yourself before I go over it myself, then the problem's in the link of the problem's in the descriptions. The link is in the description below. Guys, I ate too much ice cream and now I am drunk with sugar. That's why sugar ain't good for you. Anyways, to the problem. Given a binary tree, find its maximum depth. The maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. Note, a leaf is a node with no children. Well, that is helpful to know if you don't know what a tree is, or a binary tree, or even how to traverse a tree in general. I just came back from a recent lesson about teaching about trees and binary trees and how to travel through trees. I could go over it again. So let's go through this. 1. To find a tree, you have to go to the tree forest. Nah, just kidding. I'm gonna go straight to the point now. let's just be real now. Okay, so tree. A tree is a data structure. Basically, the concept of a tree, from what I experienced so far my whole life, is that there's a parent node with children nodes, and that children node could have children nodes. And that children's nodes could have children too, and there'll be a children's nodes of that root node. Because there'll be only that one node. There'll always be that one root node that will be like the patriarch or matriarch of the rest of these nodes. I take it back. The best way to put it is calling an ancestor, and the rest are the descendants right below it. Now, in the case of what we're trying to solve here, a binary tree, you can see right here, this is the best example you can see right here so far. This is a binary tree because each node will have at least 2 children nodes right below it. This one has 2 children, number 3 has 2 children, 9 and 20. 20 has 2 children, 15 and 7. Alright, and now you might be wondering, what does depth mean? So when you find depth, it's basically, so for every tree, when you measure how big, how deep the tree is, it goes by levels. This is the first level. That's from the root one. Second level is right here, which is 9 and 20. And the third level is 15 and 7. And you can tell that the deepest level, the farthest level it can go, is the depth of that binary tree. And so now we want to calculate that value. How do we determine the maximum depth of a tree? Now, the part that I'm most familiar with is using, let me double check this for a second, I gotta think about this. I see, okay, I think I have an idea. Now, this is going to be a bit different than, is there any hints or no, not really? So one way to solve this is that, of course, when you want to see if you're going, let's just think about this intuitionally. Pretend I'm a traveler going into a city that's structured like this, and I want to go the farthest as I can. So you go start at 3. What's the first thing I should do? I want to see if there's a path that could take me farther. Take me, like, let's just say I want to go see if it could go farther and see if there's any other paths there and see if it could go any farther from that, right? So at 3, I could see it could go farther. There's 9 and 20. I'll go to 9. Oh, it's a dead end. Let me go back. So the farthest I know if I went to the 9th, the path with the 9 is 1. So I'll go back to 3. I still have the unexplored path, 20. So let me just go to that one right now. I went to 20. Could it go farther? Yes, it can. 15 and 7. So I go ahead and do that again and go to 15. And could it go any farther? No. But what I do know is that I went 2 paths farther, and that's like the maximum distance I went so far. So the maximum depth technically here is, wow, I totally screwed this up. I start with 1, and then went to the second one, so that's depth of 2. Okay, so when it goes to 15, the maximum depth that I traveled is 3. Now, the same when I go back up here 20 and go to 7, the maximum depth is still 3. So if I were to report to my boss, my parents, I tell them, okay, what's the farthest you have went? I said 3 because I did what I just told you right now. So that's like basically, now you might be wondering, okay, that's a very long story. How does this help? This helps because, let's just say okay, hold for a second. All right, so okay, let me think about this. Wow. Ah, yes. Okay, so first, it helps because one, okay, conceptually when you write code, sometimes it helps to like picture it as a story and then try to translate that story into code. So in this case, I want to I start with the knowledge that, okay, the maximum I went to is so far none because I didn't travel to any node yet. And the maximum level I went so far is 0 because I didn't start in any node yet. But once I start traveling, and by the way, what I'll be doing is called a recursive function, and I'll tell you why. Return, traverse. This is the function I'm calling. I'm going to go and define it later. So I'm going to traverse this route. I know nothing of, excuse me. I know nothing about when traveling into define the maximum depth. So public int traverse. I'm gonna get the reference to the node, int is max, int is level. Bam. Okay, now what? So as soon as I was able to land to one of these nodes, I initialized it with 1. So I know that, I started with at least 1 level first. Now, I see if there's any nodes to the left. Okay, see? You can see how my story is playing out, right? If there's any paths to the left now. If so, that maximum will equal, we'll update to see, like, once I come back to this location right here, I'll be able to report what is the maximum paths I went so far. So maximum left. Now I'll go left. I'm going to put that node there because I'm going to go travel to that node at the left side, max level right there. And now I want to do the same thing if I want to look at the right side, actually. Reverse. No dot right. You can see. I can see. All right. Now I look at the left and the right, and now if there's a left and a right, like you can see right here, I update the level value, and plus plus plus. There you go. Now let's just say I'm at this point right here, like at 9. I see I can't go any farther now. What should I do? So now I want to check, is the max less than or equal, like the current max that I know of, less than or equal to the levels that I traveled so far, and if it's less than that, then definitely you want to update it with the maximum that you did travel. In this case, I traveled 2. See, I started here, what's 1, and I started here, that's 2. So max is equal to the level that the farthest that he ever went to when he started right here. He'll record it right there. And I'll return this max, and you can see why now I'm holding this maximum value. Now go back here again, if no dot right, so okay, I'll be doing the same thing too. I travel all the way farther, and you can see that it will update on its own until it reaches the farthest part right here. A key part that I probably should have mentioned about doing a recursive function is to create certain base conditions so that once it meets that base condition, it will stop calling. Okay, recursive functions call the function on itself, and it will keep calling on itself until it reaches a specific base condition. In this case, it will stop calling on itself if there's no nodes that can travel at the left and the right hand side. It will, once there's none to travel with the left and right hand side, it's going to go ahead and just return its maximum value that it traveled so far. So that's like the base condition. If there's no nodes to the left or to the right, it will start retracting back a certain value, whatever information it gathered, how far it traveled. Now once that's done, it goes all the way up to the point where the recursive function was first called, right here. And now return that value. Hopefully that makes sense. If not, Please leave comments below. Did I get this right? Oh my gosh. I think I just realized something. Now, you know, I should probably warn you that if you're doing interviews or, you know, solving any question at all, you have to think of all the scenarios where your algorithm could go wrong. Now, from what I understand right here, yes, of course. I mean, it even said it's accepted. And, you know, it has those scenarios, like you want to see if there's anything to the left happening or the right happening. It updates it, etc. Now, what's the one scenario here that you can see that where, you know, it could go wrong? Like, it will just fail. I'll give you a clue. One, it all happens if it has a root node to go off by. Actually, that's probably the answer. If the root is null, it cannot traverse at all. I didn't mean to rhyme there, guys. So if the root is null, then it can't travel at all. Therefore, the maximum distance you could travel, if you can't even travel there at all, is 0. You want to make sure you have that one case here. You want to make sure all edge cases are covered. I think I did cover it. Let's try this again. I just want to make sure nothing else failed before I submit the answer. Alright, I submit it. Hooray for science. Okay guys, I hope that makes sense. In summary, first I want to check if I could travel there at all. If I can, I go ahead and traverse through the trees, and I check if the left or the right, if it has any left or right branches I could travel into. The farthest I can go, I can update what that maximum value is with this certain condition right there. But once I finish traveling, it will return those values back to the first time it was called. Now, how long will this take? Excuse me. So, let's think about this. The number of space I've taken. I think how space works at this point is that since there's a bunch of it's like basically the maximum depth it can go. Worst case scenario, it's going to take about ON, I presume. And now the best case scenario, man, actually I should look up about recursion and how does that work with space complexity. Now time complexity, it's definitely going to be traveling to every single node of the tree. So I would say O of n. About O of n. I hope I got that right. Excuse me guys, pardon me, got a cough. So I hope that makes sense. If I got some parts of it wrong, please correct me in the comments below, or if you have a better solution, add it to the comments below. If you want to tell me about your life, add it to the comments below. And if you do, like and subscribe to this video. I'll give you what I need, cough drops. A bunch of them, 1,000 cough drops, so you won't be coughing like me right now and drinking and sipping water. Once you open up your mailbox, thousands of cough drops from holes will fall down into your lap. Just kidding. Just kidding, guys. I'm sorry. Alright. Thank you for watching. You guys have a good, healthy day. See you later.